in very simple way. You can see that I will discuss in my own way. Okay, let's see here. The famous equation of Heisenberg's uncertainty principle, where it denotes del P del X is always greater or equal to h cross by 2. Means del P is change in momentum of the particle, and for the same particle this is change in position along x-axis. This is Heisenberg's uncertainty principle along x-axis. We are locating the particle along x-axis. The change in position of the particle along x-axis, change in momentum of the same particle along that same axis, not in different axes. As we are calculating the position of changing position of the particle along x-axis, and we are calculating change in momentum along y-axis. No, then it won't work. It works over when the momentum and position are along the same axis, along the same dimension. And that's h cross by 2. H is the Planck's constant. Is it visible? Is there here? No one? Yes. So, as we know, let's discuss the beginning of Heisenberg's uncertainty principle, the story, why they need these things. And it's a very fundamental to quantum mechanics. As the name suggests, it explains the beginning of uncertainty in the quantum mechanics. So it tells us that there is somehow uncertainty in the measurement of the location of particle, or with respect to it, the momentum of the particle, of the same particle along the same dimension. Why the uncertainty remains there? Initially, scientists and physicists thought that this uncertainty is due to the errors in measurement or some miscalculation while calculating this. No, this is the nature of measurement. Especially can say the nature of quantum measurement in quantum world. Maybe while going deeper inside quantum mechanics in future, we can lead to the universal or perfect measurement. But now, up to now, quantum mechanics tells us that perfect measurement is not possible. You must have some of uncertainty.
Who is this? Roshan Kern is saying hi.
Roshan Kern.
At the rate Roshan Kern Roshan. They said hi.
Yeah, hi. Thanks for watching and being in my life. See you. So change in momentum and change in position. And then the question arises that for a particle, particle means extremely small particles. Let its del x is known exactly. 0 means position of the particle x1, x2 minus x1. The particle is somehow in between them, and that's the value of del x. And if you know the position of the particle exactly, then you can say that no, it's either at x1 or x2. And in that case, x1 is equals to x2 for exact location. And therefore, del x is equals to 0. Means once we locate the particle exactly to a place, then we can say its coordinates definitely, and the change in the position means the difference in the coordinates is 0. Means we are quite sure the particle is localized at a point, pretty sure. Then, due to Heisenberg uncertainty principle, del p will become del x, and that gives us infinite. Because why del x is 0? Putting del x equals to 0 here, we get del p, means momentum of particle at both the places, the difference is infinite. Means we have no guess, we have no any data to tell us that what will be their momentum, either 0, infinity. Means the gap between the momentum is so huge that we cannot tell, we cannot say that what will be the momentum of the particle. That's the nature of this. If you locate the particle exactly at a place, then its momentum will be so vast that we do not have any idea how the particle is moving. Means a large uncertainty within the velocity of the particle. How many people? Large uncertainty in the velocity of the particle, and that's the beauty of this equation. Let's see here. In second case, if you have figured out for the same particle this time we are telling you that we know the velocity of the particle v is constant. Means you can say that I know the velocity of the particle, and therefore mv is constant.
See,
Yeah.
he's telling that I don't really understand much of what's going on here, but I'm enjoying listening the way you're speaking. See, this is the topic of physics.
This is Heisenberg Uncertainty Principle. It works in high uncertainty. That is a quantum physics, a higher level physics.
Even if you are familiar with 11, 12 physics, you could understand this topic.
There's a very brief and small discussion of quantum mechanics, especially Heisenberg's uncertainty principle in the first chapter of chemistry, a structure of atom.
And also in the second 12th physics.
So see here, mv is equals to constant. If the particle v has a constant velocity, means we can say that this particle is moving with a constant velocity, a known velocity. Then its momentum is known, constant. And then we say that change in momentum is 0 because it has same velocity. The velocity is not changing. So del p is equals to 0. As del p is equals to 0, then again with the Heisenberg uncertainty principle, we are getting del x is equals to c. The dog is also barking in our life. See, h cross by 2 into del p, and del p is 0. So what we are getting here, it's infinity, reverse than this. Means once we know the particle's velocity exactly, we can predict its momentum exactly. In that case, the change in momentum means difference in the momentum is 0, and then the change in particle's position, location, means the change in the position of the particle is infinity. It means that you cannot say where the particle is, because if you say that this is one end of the existence of particle, then particle will be somehow at the other end, which is infinitely far away. That's the uncertainty. In first case, we determined the location of the particle exactly, then our momentum will be uncertain, means highly uncertain. The guess about its momentum is infinity. In second case, when we take the velocity of the particle as constant, means the momentum will be constant, means we are pretty sure what's the momentum of the particle. In that case, we got the location as infinite, means the change in its position is infinite. This nature, see, this works at all the levels. Even in classical physics, bigger physics, Earth, Sun, star, moon, galaxy, everywhere. But there, the result is so small, or such negligibly small that we have to ignore it. But inside atom, within molecules, inside nucleus, when we are dealing with the subatomic particles, there, when this Heisenberg Uncertainty Principle is vital, it's so significant that we have to take in our calculation that inside atom, or at extremely smaller level, we cannot say, or we cannot measure exactly correct. We have some errors inside our measurement. Means errors are inherent property of the measurement. You have to take it for atomic particle, subatomic particle. Means suppose you have located an electron in an atom, that this is the position of electron, means you are telling that I know this is electron here. Then you determined its position exactly. The electron is located here inside it. At the same time, the velocity of electron will be so uncertain, highly uncertain, that you have no idea how fast or how slow is it moving. And then the result is that you located the particle exactly, but the velocity is uncertain. It means that wherever you are seeing the particle is not there. And wherever you cannot see the particle goes there. Means the particle is not where you are locating, and it's not there where you are not locating. So it's highly uncertain.
Until then, there is not that we cannot measure it. It does not have a single value to be measured completely.
Yes, it's the nature of measurement. We cannot improve. Initially, scientists thought that this uncertainty is due to the errors in the measurement, or errors in the designing of the apparatus, or some laboratory fault, some miscalculation in their process or theory. But later they concluded that no, this is not the errors. This is inherent property of the measurement in quantum world. At a smaller level, you have to be uncertain about the particle's location and its velocity, and it means that we cannot locate a particle exactly well. We have always made guess, and this guessing probability, this guessing capability is the base of the quantum mechanics. That's why quantum mechanics is probabilistic, not deterministic. Means you cannot determine exactly any place. We have to be probabilistic. Means we can guess that this is the location of electron. Understood? Exactly well. So it works in quantum world. It means that where the particle is located, the particle is not there. And where the particle is not located, the particle could be there. So it's very highly uncertain. It's like God. You can say that God is everywhere, but not visible. Or we cannot predict or see God, but He is everywhere, He is everywhere. The same thing goes for the uncertainty principle for the subatomic particles here. Now see, with a common example, I'm going to explain it. Let me write this. If you have any queries Any question, any suggestion, you can ask me, you can say it to me, you can call me, or you can mention from where you are watching this live. Is there any comment?
Not yet. Just word comment. Alphabet jump 5, 6, 7, oh shitting. What does it mean?
What?
Oh shittings. I think this person doesn't like what are we going in live. Doesn't matter. Explain.
Okay. What is it saying?
Oh shittings.
Okay. Be in life.
Seems like a child. I think he doesn't understand what is the topic.
Okay, Bill, watch it. See this. Change in momentum, change in position. From this uncertainty principle, there's another form of uncertainty principle here. See, take this equation. H cross by 2. What we are doing here, I'm doing some manipulation. By multiplying del t by del t. See, this is very easier format of this Heisenberg uncertainty. I'm not going to derive it with a tedious analysis, a tedious calculation. I'm just making it handy, useful for everybody. Say this. Del p, del x, del t by del t. I have multiplied this equation by del t, by the time, changing time. See this. Now bring this here. H cross by 2. And see this. What will be this? Sorry, no, del x, but del t. See, del p by del t, change in momentum by change in time. You can watch it from, you can guess by Newton's second law also. Del p by del t is your force. Force, rate of change of momentum by time, F, del x. Now this del t, H cross by 2. This is this. F del x. What will be this? Force and the displacement. That is the work. Del t. And work. As we know from classical physics, the work is the change in energy. Difference in the energy defines the work. And so I'm replacing W by del E. See, so from the same Heisenberg uncertainty principle, we got a new equation. This is also the form of, is this visible?
Yes. Don't go far right.
This?
Yeah.
See, the different face of the same equation. What we are getting here? We are getting here, delta is the change in energy. Change in energy of the same particle, and del t here, change in time for the same particle. Now see, both the equations have the same property and same nature. Here it shows the uncertainty in the momentum of the particle and the location of the particle. Here, uncertainty in the energy of the particle and the time of the particle. Let's see. A very simple analysis or explanation of this equation, and then I will conclude something. Thanks for being in my live. You are enjoying. You can ask questions. See, it's a very easier derivation without any quantum or any tedious calculation of integration, differentiation, or just very simple, a very easier way to know to go from here to here. This is from del P by del T, Newton's second law of force. This gives us force, and force into displacement gives us force. Everybody could understand it easily. See this.
20 minutes.
Okay, that's right. Let's see. Is there anyone here? Say this. See, we came from this equation to this equation. This is del. Again, similarly, suppose a particle electron, subatomic particle electron, and you have figured it out that it existed for a time interval from t to this exist from t1 to t2. So your del t is equals to t2 minus t1. That's the time. This is the time period within which the electron exists in the given space. Electron exists. Now, using the same uncertainty principle, what we are getting? Del E as h cross by 2 del t. Understood? So you are not sure how long electron is existing. You have a time period. Now be sure, be determined that I know the electron is existing at this second at this point. So T1 equals to T2 for sure, to being sure about the electron's location and its existence in time. So then delta is 0 for sure, for surety. Surety. Del E is equal, wait, let me write. Is it visible?
I think so.
For surety of electron in time. Remember, in time means I know that suppose as 1059 electron is existing, then del T is 0, and then del E is equals to infinite. Del E will be greater than infinite, means the same analysis. Once we know that the electron or the particle, subatomic particle, is existing for this time, definite time, no two differences in time, one time, then its changing energy means difference in its energy will be infinite. We cannot say how much energy it requires to keep it into that time, to keep particle in that time.
Someone commented, yes, Raj, HK6PV, crazy bro, teaching this time.
Eat, yes, thanks for your compliment and your comment. Actually, this is the time for YouTube Live. We get more like, views, and subscriber in this time. That's why we used to earlier. See, I'm telling you my initial story. We started to be live at 6 p.m. in evening. We don't get any views. Shut the door. Shut the door. This door. We didn't get any viewers or subscriber. Then we shifted our time to 9 o'clock. Again, the same reason. But once we switched on 12 o'clock, we are getting more views, more subscribers, and our life will be better than other time. That's why we prefer to be here in this time. E2 minus E1 is infinite. Means you have no idea how much energy that particle needs to be in that one point of time. When the time of particle, when the time of the particle is fixed, you have said that the particle is existing at 11 o'clock here, means infinite amount of time needs to keep that particle in that time.
See, because
Yes.
because H ray 1, 2, 3, 5 days said high.
Yes, hi, definitely. Thanks for being in the live.
I think a lot of students used to read in this time. That's why we get so much views in this time and so much people viewing.
You can ask any question or any suggestion. If you have, you can comment us. We glad to know this. See, this will be infinite.
And
So,
if you'd like to come, if you'd like to know about some other topics, or you'd like us to come live with other topics, you can tell us, and then we'll make it possible in our next live.
yeah. And you can mention from where you are watching this live and in which class you are right now. See, means once we know the exact time of the existence of the particle, we have no any idea how much energy it requires to be in that time. Invert this, okay? See this. Now this time, try energy. Be sure in energy you will get infinite change in the
Okay.
time.
See, yes, Raj, FJ6PB.
Yes.
He is telling you, explain charging of the capacitor. Okay, it's I think a 12 level
Charging of capacitor.
charging and discharging.
Charging and discharging of the capacitor.
Tell
Now
me.
tell me, when will you be available in the live? I will discuss in that time. Tomorrow, later tomorrow, tell me. In the same time, I will discuss the charging and discharging of capacitor.
When would you like us to come with this topic in live?
Yes, we'll be in that time.
Okay, he is. I think he wants to learn it right now. I'm here.
Are you? So we are right now on Heisenberg Uncertainty Principle, and these two topics are highly different to each other. This is from quantum mechanics and the charging of capacitor from the electrostatics
Yeah.
of college, high school level, and this is at the college level, university level. So through my mind, I'm explaining this. I will explain it tomorrow if you wish. If you wish, then I will explain it tomorrow. At the same time, 11 o'clock, 12 o'clock, whatever time you tell me, after 9 o'clock, I will explain it.
Charging and discharging of the capacitor with the equations.
Yeah, everything I will teach you in entire electrostatics, magnetism, whatever you need, I will explain it. Just be on that time. Tomorrow, whatever time after 9 o'clock, you will message on my YouTube channel. I will.
He is telling no worries, you continue. We'll come tomorrow at sharp 12 o'clock midnight.
Yes.
With this topic, charging and discharging of capacitor, with the all the equations of it and derivations and questions on it. Okay.
Okay. Or we can upload our videos over the charging and discharging of capacitor
Yeah, that's
in 1 or 2 days on my YouTube channel. You can see there entire thing. Or if possible, then in tomorrow's live, I will explain it. Be on time at 11 o'clock, 12 o'clock, whatever time you can be.
We'll fix on sharp 12 o'clock. Okay.
Yes. So this time we are, suppose this is an electron, and this electron, I'm pretty sure that is the energy of this electron. Determinant, no change in the energy. Is the energy of the particle. So as we know that it has a known amount of energy, so the uncertainty in it, del E means E2 minus E1, but it has one value, so this has no importance, it's 0. And once del E is 0, then from this equation you can see that del T is equals to H cross by 2 del E, and del E is equals to 0, therefore del T will be H cross by 2 0. That will be infinite, means reverse of the initial condition, a previous condition. Here we know, we have measured the electron has this much amount of energy, then we do not have any uncertainty in the energy. Del E is 0, means one fixed amount of energy, no fluctuation, no uncertainty. Then it gave us highly uncertain time period of the electron. The electron can exist up to highly uncertain. It will exist up to infinite amount of time. In the previous case, we did that. We have taken the time period of electrons fixed. Means we know the electron existing at this time here. So del T was 0 at that time. Then del E was infinite. Now del E is 0, so del T is infinite. Means once we know that a particle is at this moment here, then the amount of energy required to put it there is infinite. And once we know that this particle has this much amount of energy right now, then the time it will exist will be infinite, the time period. So energy and time uncertainty. Understood the second form of this Heisenberg uncertainty principle. Now I'm switching to a third form of Heisenberg uncertainty principle in a very simple way, not in quantum way. And see, before going to the third way, I'm telling you this here. Remember, momentum is a vector, position is a vector, energy is a scalar, time is a scalar. Means, what do you think? This uncertainty principle works in both the ways. Either you are making vector measurements, your measurement of vector quantities, again uncertainty works. The principle works for subatomic particle, and as we are measuring scalar quantities, again it works. It means that within dimension, without dimension, you must have Heisenberg's uncertainty principle inherited into the measurement of subatomic particle. Yes, tell me, what is the comment?
It's the same person, Raj. Yes, Raj.
Yes.
KS6PV. He's telling that I have read this in class 11th chemistry chapter.
Yes, in the first chapter chemistry, structure of atom.
But there it was very few, it was not discussed in this much of detail.
Yes, it's in the university and college. Whenever you go, you will read there Heisenberg's uncertainty principle in the beginning of quantum mechanics.
And in the three forms, the momentum position, linear momentum position, the energy time, and the angular momentum position. But in the 11th chemistry or 12th physics, it's very
just glimpse.
Yeah,
they are just preparing you for university study. Just glimpse of these things. In the first chapter, we also teach students the photoelectric effect, the Heisenberg's uncertainty principle, the structure of atom, all these things. But in a very brief, Pauli's exclusion principle, Aubert principle, spin introduction,
and a little bit of Schrodinger's equation.
Yes, Schrodinger equation. Just a glimpse. That is just a heading of book. Inside that book, you will see these things. Even I am explaining this in easy way, not in the way the book it is in the book.
There are other interesting topics on our channel. If you like to read,
yeah, you can watch our channel. There is some your class materials also of class 12 physics and maths videos, lectures, and some of the research work. I have my research works also on this video over quantum mechanics, electron spin. Yes. What the comment?
There's no.
Okay. Thanks for being in my live. You are taking interest. You both or several people are taking interest. That's very good and encouraging for us. And remember one thing, we explain what we learned. It's not from any other video or we read the books, we read the stuff, and we try to explain it in our own way.
There are topics of electron spin and the topics of...
Even you can get the topics of electrostatic. What is electric field? What is electric potential? How forces calculated between the charges. You can get it on my YouTube channel. You can watch this channel.
And there's videos on twin paradox.
And integration, differentiation also. You can get better questions on integration, differentiation solved on my channel. See, del E and del T. See, both are scalar here and both are vector here. So even you are doing vector calculation for subatomic particle or scalar calculation. In both the ways, you have to face uncertainty principle because our quantum world is highly uncertain. Remember? So it has no dimensional. See, here the change in momentum along x-axis, then the position of the particle along x-axis, that's mandatory. If you are changing momentum along y-axis and you're locating the particle along x-axis, in that case it failed. But here, no need of direction. Del A and del T,
Okay.
they're both
There's
as
another comment. Oops. WHOOPS. But the comment is in Urdu, and sorry, I am so sorry, I cannot read Urdu.
okay. You can
Urdu or maybe in some other
give me a pen.
script.
Which SQ? Let me see.
It's looking like Urdu.
Okay, okay. Yes, it's definitely. May. Yes,
Yeah.
Urdu, Arabic,
Yeah.
Arabic or Persian. I think Persian, Arabic, or Urdu. Are you Arabic or Persian?
The person is not viewing.
Okay.
Explain in the third form. It has been
So-
26 seconds.
Third form, see here. Understood? So vector and scalar. And the third form is here. See, from del P to del X, H cross by 2. This time, I am explaining del P, del R, del X by del R. Del R is something like, this is along del X, one dimensional, and this is normal. Suppose this is in del Y, del X, then this will be in del Y. And this gives us angular momentum, del L and del theta. Del X by del R will give you del theta, H cross by 2. So change in angular momentum of the particle to its angular orientation. This is angular orientation, like position of a particle in one dimensional form. Similarly, this is change in its angular position. So these two have also uncertain relation. It came from here, but here notice one thing. It goes in a plane. Here it is one dimensional equation. It is scalar equation, and it is in a plane, because whenever angular momentum arises, it's never been in a one direction, it's always in a plane. Suppose you are going in this direction and you have some effect in, so you are going in this direction. That's why we have a motion in a plane like analysis. So whenever angular momentum arrives, think that it's a plane, not a straight line. So del X and del theta, and once this, like this, see, a particle is moving in this direction, there is some effect and it changes into it. So now this is along, this time y and x, it's in a plane, and once it goes in a plane, it has some of the changes in its angle, and that's why change in angular momentum is related to the change in its angle. This also gives us uncertain relation like this too. And once you understood this too, you can understand this very easily, and I will explain in any other video. Because it comes in a plane, it will need some better explanation. Now I'm going to
It's been 40 minutes.
40 minutes. Okay. So that's the explanation of Heisenberg Uncertainty Principle in a very easy and simple way, relating to its importance in quantum mechanics. And this third form is left here. I will explain it in any other video, or maybe in next live, when I will discuss what will be the expectation value and what is the eigenvalues of a particle's momentum, energy, location. Then I will explain this third term, and then I will tell you that why quantum mechanics is so uncertain due to help of Heisenberg. Once you got one thing in this life, that Heisenberg's uncertainty principle is inherent property of the measurement of subatomic particles, and that's why we have always an uncertainty related to the measurement of particles inside an atom or extremely smaller level. And due to those that uncertain measurement that affects the entire study, and that's why quantum mechanics is uncertain. Now in detail I will explain why quantum mechanics is so uncertain, what is expectation value, and what is eigenvalues, what are differences between expectation value and eigenvalues, and there I will explain this third form of Heisenberg's uncertainty principle. So for then, thanks for watching and thanks for being in my life. If you have any question, any query, you can comment me. You can watch my channel for physics and maths videos, especially our research works. And if you have any doubt or any suggestion, you can message me. I'll be glad to know this. Thanks for watching. Ended.